When we digest proteins in our body, we first hydrolyze their peptide bonds to obtain smaller protein fragments. This reaction is very slow at physiological pH unless you add a catalyst. Chymotrypsin is such a catalyst acting in our intestine at slightly basic pH. In this schematic depiction, we are showing the enzyme in blue zoomed in on the active site. The labeled serine and histidine side chains have crucial roles in catalysis, as do the main chain hydrogen bond donors shown. Chymotrypsin cuts peptide bonds C-terminal to aromatic side chains, which bind in a hydrophobic pocket. The catalysis occurs in multiple steps with the enzyme covalently bound to parts of the peptide as it gets hydrolyzed. First, the oxygen of the serine side chain attacks the carbonyl carbon of the substrate, aided by histidine deprotonating serine, making it a stronger nucleophile. The resulting tetrahedral intermediate carries a negative charge on the oxygen, stabilized by hydrogen bonds in the oxyanion pocket. Next, the carbonyl double bond forms again, and the former peptide bond breaks, aided by histidine acting as an acid to protonate the nitrogen, making the C-terminal part of the substrate a better leaving group. The second half of this mechanism, just like the first, is an addition-elimination reaction. Now, however, water is the nucleophile and serine is the leaving group. The oxygen in water attacks the carbonyl carbon of the intermediate, aided by histidine deprotonating water, making it a better nucleophile. The resulting tetrahedral intermediate carries a negative charge on the oxygen, stabilized by hydrogen bonds in the oxyanion pocket. Next, the carbonyl double bond forms again, and the bond with serine breaks, aided by histidine acting as an acid to protonate the serine oxygen, making the serine side chain a better leaving group. Now that the N-terminal part of the peptide is no longer covalently connected, it dissociates from the active site, opening it up for the next round of catalysis.